So let us start our lessons today. When a charged particle is moving in a magnetic field, so already we had started discussion on this topic, uh, motion of charged particle in a magnetic field. But today we'll see a special kind of motion in a magnetic field. That is, uh, okay. So I think if people have already read from the textbook, and if I ask you, uh, when there is a magnetic field around a region, and through that the charged particle is moving with the velocity. Suppose charged particle has charge q in velocity v. So what will be the force experienced by this charged particle due to this magnetic field? This is uniform magnetic field pointing into the paper, okay, pointing into the paper, plane of the paper. So we have discussed last in the last class that the force, which is magnetic force on the charged particle, will be written as q into v cross b. And that day we yes, that day we had learned how to find out the direction of the force as well. Okay, so that day I had not told you about the cyclic rule. First, let me just tell you that, then we'll go to the subject matter today. Cyclic rule of cross product, and this is only valid for Cartesian coordinate system. Okay, I think, I'm sorry, it can be valid for any coordinate system like r theta phi, like cylindrical coordinate system, as well as like any uh, rectangular coordinate system. That means when you have suppose coordinate axis, I'll just take an example as Cartesian coordinate system. Okay, so suppose this is x direction, this is y direction, and this is z direction, and you people know that each direction is uh, actually assigned in a unit vector. Suppose in the x direction the unit vector is I cap, y direction it is j cap, and z direction it is k cap. Okay, this is j cap in the y direction, x cap in the x direction, and k cap in the z direction. And look, these axes are actually mutually perpendicular to each other. So any coordinate system you take, whenever there is a uh, like there are axes perpendicular to each other, if you go for spherical polar coordinate system as well, spherical polar coordinate system. So if situation comes, I'll discuss. So in that case, the coordinates here, the coordinates are x, y, z. In that case, it will be r, theta, and phi. Okay, these are also actually mutually perpendicular to each other. So in this case, also cyclic rule can be applicable, but for the time being, uh, at least up to your level, we'll be applying cyclic rule of cross product for this Cartesian coordinate system. Let us see what this cyclic rule is saying. See, cyclic rule is saying that if I write I cap, j cap, and k cap like this, okay, j cap like this. So, and if you go from I to j like this, actually generally we have to go in a clockwise direction like this. So if I take cross product from like with the cross product of I and j, then according to cyclic rule we should get k cap. So if we go in the same direction like j cross k, then we should get I cap. Similarly, if I go k cap cross I cap, then I should get J cap. But if I go opposite direction, anti-clockwise anytime, suppose let us take K cross J. So this is anti-clockwise, K cross J. So this will give you, see, K, J, I'll get I obviously, but with a negative sign. Similarly, if I go J to I, J cross I, I'll get K but with a negative sign. So this is actually cyclic rule. So this will be applicable while solving problems in this chapter. Okay, not in this chapter only. This can be applicable anywhere. So this cyclic rule of cross product with the unit vectors of a Cartesian coordinate system. Okay, so this cyclic rule, I'll clean everything. I'll write properly once again. So I, J and K. So this should be like this. It go like this. Okay. So I cross J will give you K cap. Okay. Similarly, if you go from J to K, it will give you I cap. If you go from K to I, then you will get J cap. Okay, with a positive sign. If it is going opposite way or anti-clockwise way, look, if I go K cross J, I'll get I cap but with a minus sign. Similarly, all others, if you write in the opposite direction, you will get like this. Okay, so this is the yeah. So this is a useful rule of cross product with the unit vectors in Cartesian coordinate, which we'll be using frequently in this chapter, basically. Okay. So now let us see. I have told you that uh, the magnetic force on a charged particle which is moving in a uniform magnetic field, okay, and having charge q, suppose velocity of the charged particle is v. So this is the force direction of, so this is the force, this is the vector notation of the force. Okay, if I write, if I want to get the magnitude, I'll get q v b and sine of theta. So this angle is the angle between v and b. Okay, so now look, if a charged particle enters in a region, so here these are the cross. Okay, these are cross, means in this region the magnetic field is going into the paper. Okay, here in this screen, here you look in this screen, suppose the magnetic field is going into the screen. Okay, so this cross means that. Now if a particle charged particle, I think it will be better if you think that this the magnetic field is going into the paper, and suppose we are in a region, this is a horizontal plane, and magnetic fields are going into the vertically downward. Okay, if you think in that way, it will be better. Now what is happening, that the charged particle here is moving with a velocity v. Suppose this is a charged particle, positive charged particle. Okay, and look, if I see, the direction of the velocity is already given. So suppose this, I'll just take here, this is going into the page of the paper. Okay, and suppose here motion of the charged particle is horizontally, see, upward direction, horizontal, in the horizontal plane, in the horizontal plane. Now if you write, so this is v, and v is actually into the paper. Now see, if I apply our right hand thumb rule, okay, right hand thumb rule for cross product, that means I have to stretch my 4 fingers along the direction of v, because I am going to find the direction of the force, which is v cross b. Okay, direction of the product v cross b. So as you know, v cross b, if they are perpendicular, see, I know the cross product actually, if I have a cross b, then if the product of a cross b is c, c will be perpendicular to the plane in which these a and b lie. Okay, that is the thing. Now in this case, a and b both are perpendicular. both are perpendicular. One is going into the space, another one on the horizontal plane. Now, if I apply my right hand thumb rule, you look, you have to stretch your fingers along the V direction and curl that fingers, all four fingers, towards down, okay, towards down. Then the direction of force you get exactly this one. Look, it is shown here also, and I'm showing here. So this is the direction of force you get. Okay, this is the direction of force you get. All right, this is the direction of the force you get. Okay, if you are not getting, then that means you are applying your right hand rule in a like wrong way. Okay, in the last class I had discussed how to demonstrate this right hand thumb rule. Better you go and watch that lecture once again. Okay, now see see, we have learned in the 11th standard, work done is actually a dot product. F dot S, S is the displacement, and S is the displacement, S, and F is the force on the object. If the object is moving in the direction of the force, or in any arbitrary direction, suppose this is the direction of force on an object, okay, and the displacement also in the same direction, then the angle between the force is actually, so this would actually give you Fs cos theta. So this will be maximum work done. So you might be thinking, sir, why you are talking about this work done over here? Yeah, there is a purpose. See here, dot product. See, work done is actually Fs cos theta. So it depends on the angle between F and S. That means if this is the direction of force and displacement is happening in this way, and if this is the angle theta, then I need to take the component of the force along S, or I have to take the component of displacement along the force direction. Okay, let us see this angle theta. If this is 90 degree, so you will get zero work done. So actually, this is what I am just going to tell you here. When a charged particle enters into a region where there is a magnetic field perpendicular to the direction of the velocity or direction of the motion of the charged particle, then the charged particle will experience a force, and that force will be exactly perpendicular in the perpendicular direction. Okay, in the perpendicular direction. So if that is the case, then there is no work done by this force on this charged particle. There is no work done by this force on this charged particle. So then you might be thinking, sir, what does it? How does it matter? Yeah, it matters. It matters because that force and the work done on the object by that force actually uh, actually affects the motion of the charged particle. If it is not working at all on this object, then the object will be actually with the uniform velocity, it will be moving with a uniform velocity. With a uniform velocity, the motion will not be changed. The velocity of the motion will not change. So how does it matter? And look here, see in this you can clearly see that if the charged particle is moving with the same velocity v, so it is going like it as it is progressing. As it is progressing, the force is actually pulling it inward this way in the leftward direction. Okay, in the leftward direction, right? And see this force eventually will give you the centripetal force. So here I can write this as Q into V cross V, since V and V are perpendicular to each other. So I'll get the magnitude QVB. This is the force. Okay. So this force, since V and V are perpendicular to each other, you look at each and every point of this, like each and every point as the charged particle progresses in this region of this magnetic field, it will experience a force which will give this charged particle a centripetal force. And you know centripetal force, what it does? It will compel the charged particle to move in a circular path. Okay, that is the role of centripetal force. So as it go here, see here also the direction of the force will be like this, velocity will be like this, and the force will be like this. So here also it is shown. See, the velocity, direction of the velocity of the charged particle is this, but with the same velocity. Linear velocity does not change. Linear velocity, magnitude of the linear velocity does not change in a circular motion. What changes is the direction, and that direction, that change in direction will give you the centripetal force actually. Or, yes, centripetal acceleration. Okay, understand? Okay, so in this case, this magnetic force on this charged particle will be acting as centripetal force, and hence the charged particle undergoes a motion circular motion. Okay, so at what condition? When the charged particle is moving perpendicular to the direction of the magnetic field. Okay, at that condition the trajectory of the charged particle will be a circle. Trajectory of the charged particle will be a circle. If that is the case, let us see, we can find out few things like, see, they may ask you to find out the radius of the circle. So how do you find out? So I'll write from the mechanics, you know, mv square by r. That is this r is the radius of the circle, and that is actually this centripetal force is supplied by qvb. So from here 1v goes, so you can find out r mv by q into b. See, this radius of the circle depends on the momentum. Okay, with which velocity initially it started. If it is a small velocity, a small momentum, the radius will be small. If it initial momentum or the velocity is more, then it will be more. And if the magnetic field is increased, then the force, see, it will be pulled too much, so that the circle will be having a less radius. And also if the charge is more, then it will be radius will be less. So this is the way you can find out. Now see, from here many things we can find out. We can find out, so if with this itself I can find out angular frequency, linear frequency. So those things will be like, so actually this is one of the uh, property with which the cyclotron is actually cyclotron, which we will be learning today. Cyclotron is actually constructed. Okay, so okay, so this is one thing, when the charged particle is moving perpendicular to the magnetic field, so then there will be a circular path. Okay, trajectory of the charged particle will be circular. Now if suppose the charged particle moving uh, in a region, suppose the magnetic field, as you can see from here, magnetic field is along x direction, and charged particle is moving like this with the velocity like this. Okay, this is the direction of velocity. So you can see, I think I had already discussed, I don't know whether I had discussed. So there are two components of this velocity, one along the direction of field, so which I can write parallel component, and another one along the direction perpendicular to the magnetic field. Okay, so now what will be the trajectory? So in this case, what will be the trajectory of the charged particle? How to find out that? Look here, what happens? See, I have seen that the force, magnetic force, is actually q into v cross b. Okay, now q, v, b, and sine theta. So if this theta is 0, then what is the force on the charged particle? It is 0. That means the velocity component, which is parallel, or if it was even anti-parallel, the force, see, either 0 or 180°, that will give you 0 force. Okay, that means the component, velocity component, which is parallel to the magnetic field, will not be affected by this magnetic field. Okay, so the charged particle will be actually dragged towards x direction by this v parallel. Okay, by this v parallel. But another component is there, that is v perpendicular, which is perpendicular to the magnetic field direction. So this will actually experience a force due to this component. So that will give you centripetal force, isn't it? Because this components are perpendicular to, say, v perpendicular is perpendicular to b. So this will experience a Lorentz force, which will be actually, as I told you, that the perpendicular component will uh, experience a force such that the charged particle should undergo a circular motion. Okay, if I take the effect of both individually, one is actually experiencing a force, this perpendicular component, which actually demands the charged particle to undergo a circular path, but the other one, which is parallel to the magnetic field, actually demands the charged particle to go along the direction of charged particle. So if I just combine these two tendency, what I get is a helix. That means, see, the charged particle, in fact, the charged particle will move along the direction of the magnetic field or parallel to the magnetic field, but not in a straight path, with a helical path. Look here, charged particle from here, it was actually due to v perpendicular, it will try to make a circular path here. Okay, try to make, but before it completes the v parallel, okay, before it completes the circle, v parallel will push it towards the right. Okay, that's why instead of completing a circle, it will go like this. Okay, go like this, like a helix. Okay, I think this figure is fine. Okay, so if you go like this, so it will be like this. Okay, so this is the helix, and see, the helix has actually kind of, see, it is rotating, it is going all the way here, then it is coming here. Okay, so it is actually uh, but you will be surprised that the radius of this path, if since it is actually a circular path, but it is moving, so radius will be the same as the circular, like, see, if we write mv square by r is equal to q v perpendicular into b. So from here you can find out the radius of this, okay, helix. And one more parameter you have, like, sometimes people will ask you to find out for this, what is the pitch? What is pitch? See, a charged particle is moving like this, okay, and so, see, before it completes the circle, see, in a time period, see, circle should see, if the circle is moving like this in a, like, completes a revolution, then the total time it takes to complete a revolution is called time period. Okay, so in this case, the time period is same. Time period is same for helix also and the circular path also. So if you have been asked to find out the time period for a helix, then what you have to do, you have to take the v perpendicular and use mv square by r is equal to q v perpendicular into b. So that component, with this component, whatever radius you get from radius, you know, like 2 pi r is the total length, and you can find out the velocity. So with that you can find out t, time period. Okay, so once you get the time period, so look, uh, see, this is, suppose, if suppose the charged particle is started here, okay, has started here, so it will go all the way up to here and come here itself. Okay, and when it reaches here, one full revolution completes. Okay, that means, yeah, so this one full revolution will be completed over here. So sometimes they will ask you to find out pitch. What is the pitch of the helix? So how to find out that? So this is a straight line. Like during this time period, how much distance it travels along the direction of magnetic field? How much linear distance it travel? Okay, during a complete revolution. Okay, during a complete revolution. That means if you know the time period and look in the along the direction of magnetic field, you have parallel this component of the velocity. It is not affected by any force, so it will be uniform always. So like distance, you can find out distance if you know the time, how long the charge particle is moving, and you know the uniform velocity. So v parallel into tau, sorry, t. So this is the time period. So if you know the time period of the revolution of this charge particle, then you can find out the pitch, that is the linear distance or along the direction of magnetic field traveled by the particle in a complete revolution, during a complete revolution. So you have to actually, you will get the pitch as v parallel into time period. Okay, so then you might be thinking, sir, how to find out time period and all those things. Actually, while discussing cyclotron, we'll be discussing these things, time period and all, but still I can just develop now here itself. So suppose m v square by r is equal to q v b. So this now you can find out the b or r, whatever you want to find out, mv by qb suppose. Okay, so what will be the time period? Time period will be actually 2 pi r by v. Okay, let us just put the value of r here. So 2 pi, okay, mv by qb. So qvb. So v goes off. So you get 2 pi m by qb. 2 pi m by qb. So if you have been given what is the charge of the particle, what is the magnetic field in which the charge particle is moving. If the charge particle is given, then you know the mass of that particular charge particle. So then you can find out the time period. And if the velocity is given, and if you know the angle between the velocity and the magnetic field, so you know the parallel component as well as perpendicular component. Okay, so with that you can find out v parallel into this term. If you multiply, you will get the pitch of this helix. Okay, this is a question which you may like come across. Okay, now we'll see another part, that so this is actually the motion of the charged particle when there is only magnetic field. But we can see what will be the trajectory of the charged particle, or what happens if the charged particle is moving in a region where there is crossed electric and magnetic field. What do you mean by crossed electric and magnetic field? First of all, when there is a charged particle, like when there is a region where both electric and magnetic fields are present, and if the charged particle is moving with the velocity v and charged particle charge q in this region where there is magnetic and electric field both, then the charged particle will experience a force called Lorentz force. So this will be q into e, electric field, plus q into v cross b. Okay, v cross b. In combination, we can write q into e plus v cross b. So this is the force. We have already learned this in the first class itself. So this is the Lorentz force it will experience. Now see, cross magnetic and electric field means what? When both the electric and magnetic field, suppose in this direction electric field and this direction is magnetic field. So when they are perpendicular to each other, then this is called crossed electric and magnetic field. Okay. So when both electric and magnetic fields are perpendicular to each other. Okay. So now look, let us see what happens when a charged particle moves in a region where there is crossed electric and magnetic field. So here I am taking Cartesian coordinate system. Suppose the electric field in a region where the cross electric and magnetic field is present. There the electric field is acting in the y direction. So I can write electric field in the j cap direction. Okay, electric field is E. Okay, this is my electric field, and magnetic field is along the z direction. So magnetic field along the z direction. So this is k cap. Okay, so this is my electric and magnetic field. Now, what will be the force if the charged particle is moving along? So to see velocity v is along the x direction. That means the velocity is perpendicular to both electric and magnetic field. This is along the x direction. So I cap means, or x direction means, it is, see, all three are actually mutually perpendicular to each other. Now in this case, what will be the force? Okay, at which direction the force will act? Okay, look, I know this is the total force. This is the total force. If I just see the effect of the electric field alone, then see the force, electric force on this charged particle will be Q into E. Okay, that means the charged particle will try to move in this direction due to electric field, electric force. Okay, all right. So which is shown here. Look, and now I have to see what is the direction of this force. So magnetic force V cross, so it is Q into V cross B. So V cross B. Look, this V I can write V I cap, and this B I can write V K cap. Okay, so Q V B I'll bring out, and I have to take cross product with I cross K. And see, I know the cyclic rule I, J and K. So I should go in this way. But now see, in the cross product what I have, I cross, so this is I cross K. That means I am going opposite direction. So I'll get J but with a minus sign. So my force, the direction of force is actually along minus Z direction. So which you can see here. So this is in the, sorry, minus J direction. That is exactly opposite to the direction of the electric force on the charged particle. See the electric force, I'll just clean everything so that you can, I think this is all right for you, right? Okay, I hope this is okay for you. That, okay, I'll just clean this portion. So what you get here, that your electric and magnetic force on this charged particle are exactly opposite to each other. So see, electric force, this one is along the y direction, and magnetic force, which is V cross B, is actually in the minus J direction. This is along J direction, positive J or positive Y, and this is along negative Y direction. Now suppose if we adjust this Q V B, so this is 1. Okay, so what is the total force? Then I'll write the total force. So it is actually the Q into E, this is J cap, minus Q V B, again J cap with the minus sign I am writing. So if I just take Q common, so you get E minus VB, okay, VB into J cap. So this is the now force on this charged particle. Now look here, there is an application of this cross electric and magnetic field. Nice application. What is that application? So if I adjust this electric and magnetic field in such a way, that the electric force, that means this electric force becomes equal to QVB, magnetic force. If these two becomes equal, okay, or I can write E becomes equal to V into B, then this force, the force, whole force on the charged particle is 0. Do you agree with me? I'll adjust electric field and magnetic field in such a way that the magnetic force, the magnitude of the electric and magnetic force, because this see the direction of the electric and magnetic forces on this charged particle in this cross electric and magnetic field is exactly opposite to each other. Now, if I adjust the electric and magnetic field in such a way that the electric force and magnetic force are exactly equal in magnitude, then what will happen? They will balance each other. They will balance each other. So the net force on this charged particle will be zero. So the net force, so that means you look here, QE is equal to QVB. So these two forces are balancing each other. So then what will happen? Charged particle was moving with a velocity v. If no force is acting on this charged particle, it will continue to move with a uniform velocity v in the x direction. That means the charged particle will be undeflected, or not deflected. Charged particle will not deflect. Okay, it will not deflect. It will move in a straight line along the x direction with the same velocity, because no net force is acting on this charged particle in this uh, case. But when it is, I have to adjust electric field and magnetic field such that both magnitude of the electric field and electric force and the magnetic force becomes equal. And at that condition, look, I can find out a velocity. Okay, that is v is equal to E by B. Okay, this is a particular velocity. This is a particular velocity in this condition, which will be undeflected. Suppose you have a beam of particles. Okay, beam of particles means there are many particles, and obviously all particles are not having same velocity. Suppose v1, v2, v3, etc. And if I have crossed electric and magnetic field in this region, and I adjust electric and magnetic field in such a way that some velocity will be not deflected. Okay, so E by B, this ratio becomes equal to some velocity. Suppose the charge particle 2 has velocity v2 equal to E by B. So in that case, all other charge particles v1, v3, v5, everyone will be deflected. Depending on the strength of these two forces. Okay, but what will happen? But the charge particle with velocity v2, which is exactly equal to the ratio of E to B, will move without any deflection. So that will actually, this is called velocity selector. That's why cross electric and magnetic field is being used as velocity selector. So this principle is used in mass spectrometer. So there actually, what does this mass spectrometer do? Actually, it can detect various type of ions. Okay, suppose you have mixture of gas, helium, hydrogen, nitrogen, etc. So you have to find out what all gases are there in that, or what all ions are there in that, in a particular gas mixture. If you gas spectrometer, what will happen? If you just so if you just take the ratio in such a way that the velocity becomes equal to this ratio becomes equal to the velocity of any of these gas ions. Okay, then you can detect that particular ion. Okay, obviously you need to know the velocity of each ions, like in particular conditions. Okay, so with that you will be able to find out, or you can distinguish various ions. Okay, various ions. So this is the principle, velocity selector. This is called velocity selector. In your book it is written very nicely. You have to read the textbook and see further, and see this is the principle which was used by scientist J.J. Thomson. J.J. Thomson to find out the E by m ratio, charge to mass ratio of any charge particle. Okay, this is the this is called velocity selector. Here it is written velocity selector. So velocity selector, in the velocity selector, what you have to do? What is the condition? Electric and magnetic field has to be perpendicular to each other, and sorry, electric and magnetic field. Yes, electric and magnetic field has to be perpendicular to each other, and also the charge particle has to move in a perpendicular direction to this electric and magnetic field. And now, if you adjust this electric and magnetic field in such a way that the electric force and the magnetic force becomes equal to each other, like magnitude y, direction is exactly opposite to each other, so they will balance each other, and that thus you can find out the velocity of particular charge particle which has passed through with without any deviation. Okay, all right. So you just read this portion, and see, I'll just discuss now the cyclotron. So as you can see, the cyclotron is actually a charged particle accelerator or ion accelerator. What is this? This is a machine which is used to accelerate charged particles or ions to a high energy. So I'll just tell you briefly what is like this cyclotron and why do we need to read and all those things. See, this cyclotron actually a machine which is also called this principle is being used in particle accelerator. You might be aware of Large Hadron Collider, etc., which are the experiment uh, set up for high energy or to find out the God particle, etc. So whenever we go for investigation of internal structure of nucleus, so how to find out the structure? You have to bombard a nucleus or bombard an atom with high energy charge particle so that it penetrates all the way the atom and go to the nucleus and even penetrate that also. Okay, so that kind of high energy you need to produce, or you need to produce a particle having that much high energy to penetrate an atom and go all the way up to nucleus, even that can penetrate the nucleus also. So how to create such high energetic particle? So for that, the particle accelerators are used, and in that particle accelerators, among all those particle accelerators, cyclotron is one among them. With this, only charged particle can be accelerated. Only charged particle can be accelerated to a high energy. Okay, so yeah, so we'll see in 1934 this machine was discovered or constructed by E.O. Lawrence and M.S. Livingstone while they were investigating the nuclear structure. Okay, so now what we'll see, we'll just see the structure or the construction of this cyclotron first, then we'll just go to the real physics, what is happening in that. Okay, so look here, actually both electric and magnetic field, as I told you, that cross electric and magnetic field, here both electric and magnetic field, cross electric and magnetic field is being used. Okay, cross electric and magnetic field is being used. Okay, so I'll tell you how it works and all I'll discuss. Okay, so in this case, this is even called sometimes particle oscillator also. So in this construction, you look, so you have both. See the dots are actually telling you that the magnetic field in this region is coming out of the page, That's why I'm giving this direction. Okay, coming out of the page. Okay, and look here, you have actually two metal container, like see how it is, kind of this. Okay, one metal container is like this, another metal container exactly of the same size. If you take a sphere, kind of a sphere, and cut middle wise, okay, how you get, so that is the structure actually. Okay, that is the structure. You get two such structure. These are almost actually having a structure of D. That's why these are called Ds also. Look here, there are two metal containers kept side by side with a certain gap. Look, this one. This is one D. This one. Okay. This one. And another one is this one. This is actually made from the same metal sphere, hollow metal sphere. Okay, hollow metal sphere. If you cut in bit like in the middle, so you get this. So these are having the shape of D. That's why these are called Ds. Okay, these are called Ds. So now what happens? These Ds are actually in this magnetic field now. Okay, in this magnetic field, and you have a region here. This region actually, this is a gap. Okay, gap between these two Ds, and you have a charge particle container, some charge particle container over here, denoted by P. And this is in fact actually, this charge particle is actually inside some of the Ds, inside some of the Ds. Okay, inside some of the Ds. Okay, now another D is here like this, like this. Okay, suppose charge particle is one of the Ds, and magnetic field actually, according to this, actually if I just draw in vertical position, I'll show you in fact how it is. So charge particle is here, and there is a gap between the Ds. So you might be thinking, sir, where the magnetic electric field is acting now. See, the magnetic field is actually coming out of the page. If these two are in the vertical direction, if you rotate this, okay, vertically, like this and like this. Okay, so magnetic field is like this, like this. Now in the gap region, so as long as the charge particle is actually inside the Ds, it is not acted upon by electric field. Only when they cross this gap, they come near this edge of this Ds and cross this gap, they will actually, the charge particle will be acted upon by the electric field. Okay, an electric field actually can reverse its direction. It can reverse its direction. We use actually oscillating electric field here, oscillating voltage, such that it can oscillate its direction. Okay, I'll tell you what is the situation, like when I'll discuss, I'll tell you. So this is a construction. So you have two metallic Ds. I'll just show you another figure, so that will give you right idea. So look, this is the permanent magnet, north pole of that. Actually, it is magnetic field in this way out, but I just wanted to show you the vertical figure. This is the original structure in our instruments. So these are the Ds. Okay, these are the Ds. See here, there is a region where charge particle is kept, and obviously you know the magnetic field is like this now, and throughout the region the charge particle is like this. Okay, now if the charge particle is here, and it just when it goes into the Ds, it is acted upon by a magnetic field which is perpendicular. So this is suppose the direction of the charge particle, direction of motion, and this is the magnetic field, or maybe this way. So what it will do actually, it will undergo a circular motion. It will deflect like see, it will try to undergo a circular motion inside the D's. So when it tries to undergo a circular motion, see, it has to actually, it starts from here. So it has to actually start from here and goes in the D, and see, when it completes its half of the revolution, it is coming at the edge of this D's. So it has to cross this and go here to complete the circular motion. Okay, but what happens when it comes exactly at the edge? Then to cross this, there is an electric field. At that time, electric field will be switched on, and when the charge particle at this region, so the potential will be, or electric field direction will be in this way, such that the charge particle will be, suppose this is a positive charge particle, so that it will experience a force, linear force in this direction, and the charge particle will be actually deflected, or will be thrown from D1. Suppose this is D1 to D2. Okay, it will be thrown to D2. Okay, so during this jump from one D to another D, in this gap region only, the electric field will be experienced by, the effect of electric field will be experienced by the charge particle. Now look, when I am actually trying to have a complete revolution. So once it actually comes here, so so it starts, suppose it starts from here in the D and come here at the edge. Then what happens actually? Since the electric field is on, and this gap will be crossed by the charge particle due to the force, linear force given by the electric field, and this is the extra energy it is actually gaining over here. It is gaining some energy. That means the radius of the charge particle, okay, will not remain the same as it was here. Suppose it was R. Now it will not remain after just crossing to D2. It will go like this again. Okay, again it will go like this. So it will be a kind of a spiral. Okay, I'll just repeat this concept again. I'll repeat it here. Look, see, it was, suppose in 1D. So it will start from here, suppose, okay, and go like this. Once it reach here, there is a gap. In this gap region, when it tries to cross this gap region, so look, this, it starts from here, suppose. When it actually crosses the gap region, it is actually acted upon by electric field, and the electric field is working on this charge particle. Electric field is working on this charge particle. So that work done will be stored as kinetic energy. That will give you the kinetic energy. So the energy will be increased once it reaches to the second D's. Okay, then now the radius has got changed, so it will move in this path up to here, and again electric field will give certain force, okay, to jump to this, and upon this actually when it reaches here, its kinetic energy again increased. Okay, so its energy increased. So since the energy, kinetic energy increases, the radius of the path also increases. So like this, every time whenever it is crossing this D's, one D to another D, it is gaining some energy. And look, it will be having a path like a spiral, like this. Okay, so, and each radius with increased energy, but the frequency or the time period of revolution doesn't change. It does not depend on the radius. It does not depend on radius, neither it depends on the energy. Okay, time period or frequency also. So the frequency does not change. Okay, frequency does not change. Okay, so as it actually going in a higher and higher radius, it is gaining higher and higher energy. And look, when it reaches our desired energy for the experiment, see, that means when it reaches to the highest radius of this D, then the charged particle is actually deflected by another magnetic field so that it goes out of the D, okay, through the exit. I'll show you here in your figure which is given in your book. Look here. So this is how. So this is D1, this is D2, and look here. Actually, electric field is only acting in this region while jumping from here to here or jumping from here to here. Other time, electric field is off, or the electric field is not actually affecting the charge particle or motion of the charge particle. When the charge particle is moving inside the disc, it is only acted upon by magnetic field here, okay, and each time when it is crossing one D to another D, it is acted upon by electric field and getting extra energy each time, so that its radius also increases and the trajectory becomes a spiral with increasing energy, but the frequency or the time period does not change with energy or with increasing radius. Now when the radius of the spiral becomes actually exactly equal to the size of the D or the radius of the D, then charge particle is deflected by this deflect. This is also a magnet. This will deflect the charge particle to go out through this exit port and with a high energy. This high energy particle now is directed to the experimental hearth where my matter is there, which has to be heated by this charge particle, extremely high energy charge particle. So when it heats, there will be a reaction, and obviously all the results will be analyzed by the scientists, and various instruments are involved in this experiment. This is called high energy experiment, actually high energy experiment. Okay, this is high energy experiment. So this is how this is working. So one more important point which I have not told you, you might be thinking, sir, since the electric field is only acting when the charge particle is deflected through the gap D1 to D2 or D2 to D1, then your frequency must be adjusted in such a way that when the charge particle come here, then only the electric field gets switched on, and also the direction of the electric field has to be adjusted in that way. When suppose the charge particle at this edge, so D1, so the electric field, direction of the electric field has to be like this, okay. So electric field means there is a potential difference, okay. So this has to be high potential and this has to be low potential at that time. When it reaches here, your signal has to change in such a way that now this D2 has to be at high potential and this has to be low potential, such that the charge particle will have a force, and how much energy every time it gains, that is Q into V. V is the potential difference across these two discs, and Q is the charge of the charge particle, okay. So this much energy will be added each and every time, okay. In a complete revolution, it will be actually 2 times it will gain energy, okay. And the frequency of this charge particle will be exactly equal to, so this is frequency, cyclotron frequency, suppose frequency will be exactly equal to the applied voltage frequency of the applied voltage, okay. So which is giving you alternating applied voltage. So this has to be synchronized such that when the charge particle is there, it will be having a high potential, this will be having low potential. At the same time, that means each T by 2, it has to actually change its direction, okay, change its direction, okay. So I hope you have understood this. If you read this, you will be able to understand again from your textbook. So I think this is already the time. I'm not going to take time anymore. So what I can do is, I'm just giving you the task to you people to find out this time period, and this you can just apply the mv square by r is equal to q v b like that, and whatever I have to say, I have already discussed everything in that. Now what you have to do, you have to find out the expression for the kinetic energy, and in this, and also you have to find out the frequency, etc. So those things you just try to develop. What we'll do in the next day, we'll take up few example problem depending on the magnetic force first, depending on cyclotrons, Lorentz force, etc. In the next class, and then we'll proceed further. Okay. So you guys should read up to this cyclotron. Okay. You people should read up to cyclotron, and then we'll discuss further. Okay. So see you people on Sunday again at the same time. I'll stop the class here now.